All right, question 6 is asking us to compute what's known as the Gaussian integral, and this is the integral of the function e to the negative x squared from 0 to infinity. Okay, so you'll notice I put a little star next to this question. That's in part just because I really like this integral. It's also because the result shows up in a lot of different areas, like in math, physics, statistics, the list goes on and on. Okay, so it's a really important result. And also the derivation we're going to present here is just really cool. Okay, so I will say outright, I would expect you to come up with it on your own. Okay, I wouldn't be able to do that, but it's definitely worthwhile to follow the argument. Okay, now you might also just wonder, why is this problem even in here? This is not a double integral, right? Why can't I just compute the antiderivative and then just take a limit, right? Well, the fundamental roadblock to that approach is that it turns out, this is a result that's been proven, but there is no elementary antiderivative to this function, e to the negative x squared. So no matter what uh, integration technique you try to apply to this thing, you're not going to get anywhere. In fact, it's been proven you're not going to get anywhere. Okay, so we cannot apply Calc 2 techniques to computing this thing. Okay, so the trick is to actually do some things to it and bring in double integrals into the picture. Okay, so on our way to doing that, we're going to start out by first just labeling the integral I, and then what we're going to do is square this integral. So we're going to square I, okay, and here for emphasis, I'm just going to write this as the product of the integral with itself, okay, and since these are definite integrals, the variable of integration doesn't really matter. So if I change the x to say a y or a t, the numerical value of the integral would not be changed. Okay, so what I'm going to do now in this next step is relabel the variable of integration in the second integral as y. Okay, and so now if you recall from sections 14.1 and 2, we had this result that said if you have an iterated integral and your integrand is the product of two functions where one of the functions depends only on x and the other depends only on y, then you can write that iterated integral as the product of two single variable integrals. Okay, well, I have the product of two single variable integrals, so now what I'm going to do is put them together as a iterated integral. And here, these exponential terms will multiply. By properties of exponents, then, I'm just going to add these exponents, and I'll go ahead and factor out the negative. So we now arrive here. Okay, so does this help? Well, maybe not at first glance, okay, but it actually does, right? What's our region of integration? Well, x and y are both varying from 0 to infinity. So just like we saw in question 5 there, we're integrating this function, this exponential function there, over the first quadrant, okay? And so I also see an x squared plus y squared up there in the exponents. So that kind of suggests maybe we should be thinking polar, okay? So in polar coordinates, to describe our region of integration, okay, this is just like what we saw in question 5. Okay, we can first think, all right, fix a theta, which is just going to describe a line through the origin. And now r is going to vary from 0 here, just at the origin, and then r is just going to become infinitely large as we follow this ray right out into the first quadrant. Okay, so the bounds there on r will go from 0 out to infinity, and theta is going from 0 to pi over 2. Okay, so can describe the region in polar. And so now let's go ahead and write this as a polar integral. This is going to be the integral from 0 to pi over 2, and then the integral from 0 to infinity. And then I'm going to have e to the minus r squared. And then dx dy, that's just our dA element. And we know in polar that is r dr d theta. Okay, so looking at this now, notice the integrand does not depend on theta. So just like we've been seeing with a lot of these problems in this section, this r integral here is just going to be some number, and it's independent, right, of theta. And so you can think about it coming out in front, and then the integral from 0 to pi over 2 of just d theta, that's just going to give us pi over 2. So in other words, I have pi over 2 times the integral from 0 to infinity. And I'll go ahead and write this as, no, I'll just leave it, sorry. It's all fine, just as it is. Okay, we have that. All right, and so as I said up here, the integral of e to the negative x squared, right, is not expressible in terms of familiar functions. In other words, this function does not have an elementary antiderivative. But see, now in this integrand, right, r times e to the negative r squared, I have some help, right? This r out front is a lifesaver, because now if I make a substitution, let's say I make u r squared, then du is 2r dr. So this r dr is in fact du over 2. Okay, so what's that going to give us? It's going to give us pi over 2 times the integral, and I'll go ahead and change the bounds. If r is 0, then u would be 0. And if r is approaching infinity, u would also approach infinity. And then I'm going to have e to the minus u. Sorry, that doesn't really look like a 0. Okay. And then r dr is, we said here, du over 2. Okay. So I can factor out that half. So that's going to give us pi over 4. And then the integral of e to the minus u would be minus e to the minus u. And we're going from 0 to infinity. And now if I take the limit of e to the minus u, as we let u approach infinity, that's going to give us 0. And if I plug in 0, I'm going to get a minus 1. So in fact, this is going to equal pi over 4 times 0 minus a negative 1. And so that's just going to equal pi over 4. Okay, now be a little careful here. Is pi over 4 the value of our Gaussian integral? Not quite, right? Remember, this is actually the value of I squared. So in conclusion here, this is the big conclusion. I, which is just the integral from 0 to infinity of e to the minus x squared, this is going to be the square root of pi over 4, which you could also write as the square root of pi over 2. Okay, so that is our big result. Pretty cool, really, and very ingenious as well, right? So, you know, I said at the beginning, you know, this integral shows up in a whole bunch of different areas. Now, some of you might have taken statistics at some point, and if you have, you likely would have talked about what's known as the normal distribution. Okay, so I'm not going to go into much detail here because this is not a statistics class, but I do want to point this out that for the normal distribution, this is what people commonly refer to as the bell curve. Okay, what's called the PDF, the probability distribution function for the bell curve, thing that describes this green bell curve, is this thing, which looks pretty intimidating, like so many of the expressions you see in statistics. That's one reason why people are intimidated by statistics. But really all this thing is it's essentially this e to the minus x squared function, right? Notice I have e to the minus 1/2, and then an x minus mu over sigma quantity squared. But this is really just e to the minus x squared, essentially, with a whole bunch of just clutter, okay? In the clutter stuff, mu is the mean of your variable x, and this sigma here is the standard deviation. Okay, but the use of this thing comes down in looking at, say, the probability that your variable, whatever it is you're studying, say, something like blood pressure or something, um, the probability that your variable would fall within certain bounds is related to the area under this profile curve here, this exponential thing here. Okay, so, and you see this square root of 2 pi out front. Okay, that actually is related to this thing that we just computed. I mean, there's obviously some details here I'm leaving out, but this is one of the big applications of this result, and maybe something that you would see in a future course. All right, so we'll stop there, and I'll see you in the next video. Thanks.